Great. Well, thanks everyone for organizing this. I'm going to talk today on, yes, I actually forget the title I told you and I end up using the title from our paper. But yes, so pretty much it's the same idea. So two-dimensional bifunctor theorems and distributive laws. And this is joint work with Graham over there and then also someone called Jose Siqueira, who is not over here. Okay, so what do I mean by bifunctor theorems? So I mean theorems that end up being somewhat similar to this bifunctor theorem of categories, which I think is the first theorem proved in categories for the working mathematician. So that makes it really important, probably. So here's the idea. Suppose we have functors. So these are families of functors. So we've got these LCs from B to D. So I'm using pink here to represent categories and green for objects and functors and stuff. So we've got these families. So this L family of functors that are indexed by objects of C, and this this M family, which is indexed by objects in B. And they satisfy this property that LC of B is equal to MB of C. Okay, so that's our starting point. Now, pretty much what this shows is that there's some sort of compatibility going on between these two things. And we're going to want to exploit this and to represent, essentially find a bifunctor from which we can recover this family in the following way. Right? So we'd like to find a bifunctor, P, from B cross C to D, such that we get LC by simply fixing a C object in the right component and leaving the first blank, and the M functors by fixing an object in the left component and leaving the other open. So there is such a functor if, and only if, we have that for every morphism, or every set of two morphisms, F and G, two morphisms, not in the two categorical sense, I apologize. So for every morphisms F and G, we have this equation is satisfied. And I'll explain the intuition behind this equation in a second, but we'll just see that when this equation is satisfied, we have that P of BC is equal to either LC of B or MB of C, because those are equal, it doesn't matter which we pick. And P of F comma G is equal to, now we can pick either the left or right-hand side of that equation above, because again, they're equal. So where does this come from, this that equation? So the idea is that we want to define this P of F comma G, which is going to go from P of B1 C1 to P of B2 C2. And remember, all we got to begin with are this L family and this M family. So there are kind of two approaches we can take. So the one is to begin by fixing the left-hand object and applying G in the right hand. And then again, then kind of swapping it and now fixing the object in the right hand and putting F in the second. But notice that we've made this arbitrary decision of which to use first, F or G. So alternatively, we could have fixed the C object and applied F first, and then fixed the B object and applied G. And we just want that these two paths by which we could define this are the same. And so that's where that equation comes from. Okay, so that's our starting point. Bifunctor theorem. So actually all of this research resulted from actually needing kind of a concrete form of this theorem, but for pseudofunctors in one of our papers. Actually in the paper related to the work that Graham spoke about in his last talk.
Can you say a little bit about that? I'm always interested in why you need.
Yeah, so what we wanted an ext functor basically for toposes. So we were kind of looking at this view of Artin-Gluings of toposes as being like extensions. And then we basically wanted an ext functor for this in both components. And usually it's really obvious to define it when you fix the one component, and it's obvious when you define it when you fix the other, but it's a bit hard to kind of just out of the blue define it for both. And so we wanted to merge these two obvious families of functors that we got. And so we needed this, and we thought it would be like a small little result, and then it started getting a bit more interesting. And by the end, I think this paper was like 30-something pages. And I think the results are more interesting than they maybe at first appear they'll be. So, okay, so we want to now take this up a dimension in some sense. So we want to get a version of this for two categories. And so let's make sure we're on the same page about two categories. So let's recall what a two category is. So firstly, we have objects, which we might call A and B. Then we have morphisms between those objects, or one cells, as I call them here to save space. And then two cells, which occur between morphisms, one morphisms. And so the thing you should be thinking about here is the two category of categories, where we have the objects are categories, the one cells are functors, and the two cells are natural transformations. So this is this very natural setting in which this sort of stuff arises, but actually we can do, it's a lot more general than just categories that have this structure. So it's often helpful to kind of dualize this diagram we have on the left-hand side. And I mean dualize in a graph theoretic sense. So notice that that two cell, although I've written it as kind of this two-armed arrow going down, we could just as easily maybe think of it as a directed region inside, contained within these two, the space contained between F and G. So we can really think of the two cell in this diagram as an area or a region. And so what we want to do is dualize this. So we now want to treat the two cells as vertices. So notice that, in this case, these are the vertices, these are the edges, and this is the region. But now we want to flip that. So we want to consider the two cells as vertices. The one cells are going to remain strings or wires, which you can kind of, this kind of looks like a string or a wire. And the objects are now going to be regions. And so what the preceding diagram would look like is something like this. So we've got this object A and the object B, and then this morphism kind of goes up. We've got this F morphism here, and it's on the border of A and B. And so that kind of says that F goes from A to B. But we've now connected F and G with this two cell, which is now a point. And I'm not going to get into all of the kind of coherency things. I'm just going to pretty much everything just works really nicely with string diagrams. You can move around the dots, you can twist the wires to some degree, and it really doesn't end up changing the meaning of the diagram. But in terms of composition, it ends up being quite nice. So if we were to place two diagrams on top of one another, that would correspond to kind of this vertical composition of two cells. And placing the two side by side would be horizontal composition. And so that might be, for instance, how we composed a number of two cells, alpha, alpha prime, beta, beta prime. And the order doesn't end up mattering due to the interchange law. So
it's music to my ears to see you present this, because I've been trying to tell the coding theorists about this for many years, and they couldn't get them interested in it. So
these results would not be possible without string diagrams, basically, or like we'd never have noticed them. So let's look at an example of this. And this is an example which will be important for pretty much everything we go on to discuss. So we can think of it as a triple, T, mu, eta, I think, is a monad in a two category if T is an endomorphism of an object X, and mu is kind of this multiplication from T squared to T, and eta is kind of like this identity. And we want them to satisfy certain axioms. So the first is something like an associativity axiom, which I think is basically just saying if you've got three things that you're going to be multiplying, it doesn't matter if you first multiply. This over here is kind of like considering multiplying the two rightmost elements first and then the leftmost, whereas this is the two leftmost and the rightmost. And then we also have this diagram, which basically tells us that multiplying by the identity doesn't do anything. Okay, so this is the union thing. And so let's see how we would translate these axioms into string diagrams. So here we see the first one. So notice that each path we take along our commutative diagram ends up being a string diagram that we consider. So we have this, let's say, bottom path first, and it ends up being the left-hand side, I think. And then we have the top path or the right path, and that ends up corresponding to this one. And we're just saying that these two diagrams are equal. And the second one, it ends up being two separate equations, I guess. So we've got first that if we multiply by the identity on the left, that's the identity, and if we multiply on the right, it's also identity. Or nothing changes, basically. So that's what these look like. They look nice, but maybe we aren't seeing the value. This just seems like a different way of representing these things. So perhaps it's not clear that we've gained anything yet. But here things get a bit more interesting. So there's this question we can ask about monads, which is, suppose we have two monads on the same object. And now we compose S and T. So these are, remember, endomorphisms. So we can compose them. And so is there some way to equip this composite TS with a monad structure? Oh, it does say monad. Okay, good. With a monad structure. And kind of in terms of the multiplications of the original monads. So this will be doable when there exists some map, this map sigma, which goes from ST to TS, and it satisfies certain axioms. And I'll get to those axioms in a minute. But for now, so we call sigma a distributive law when it does satisfy all of these things. And yeah, okay, so let's see what the axioms look like as string diagrams. So in these diagrams, we're going to represent sigma as a crossing. So before in the string diagrams, the two cells I was representing with a pink dot. But now we're going to instead just visualize it as the one wire crossing on top of the other wire. So in this case, so yeah, what I want to stress here is at this crossing that you see over here, that is actually just sigma. And this is sigma again. And so this is what the one axiom says. Basically, it says that if we were to have these crossings below the multiplication, it's the same as having the crossing above the multiplication. And we have this kind of converse, or like kind of, let's say, reflected version as well, where now we cross the blue wire. So sorry, notice the blue wire is T here, and the monad T, and the yellow wire is S. And yeah, similarly, we can cross yeah, kind of blue underneath the multiplication. It's the same as crossing it underneath the after the multiplication is done. And then we've got two more axioms, which I won't do individually. They're just telling us that we can move the unit we can cross, the unit can cross wires, basically. So these are quite nice. Like maybe now, like at least I'm starting to like see the value in these string diagrams. But what I haven't told you yet is how so we need to now define multiplication and unit for this composite monad TS using sigma in some way. So the resulting multiplication is going to look like this, which is, I think, quite a nice, appealing looking diagram. So the unit ends up just being, I didn't write it down, the unit just ends up being kind of horizontally composing the two units. So it's just like two lines sticking down. But so here's what the multiplication ends up looking like. Yeah.
Peter, sorry, before you continue, can I ask a baby question?
Sure.
I'm still a baby in this diagram. So putting everything in a square kind of emphasizes that regions are objects.
Yeah, sure.
But now, when a line doesn't go all the way through down,
yeah,
like when it stops midway, so these two regions are now the same object that surround that line.
Yeah. So, well, in this case, just yeah, for this case, there's only one object.
No.
I'm referring to
there are means of the identity. So what Peter, I guess, didn't say explicitly is that if you have an identity functor, we just don't draw it.
Oh yeah, I was going to mention that a bit later.
So because the unit goes from the identity functor to, say, the functor T, then it's stuff we don't draw the part below the unit thing, because that's just an identity functor. So we just omit that from the diagram.
But does that mean that these objects are the same now on the left side and right side?
Yeah, they must be, because it's the identity that would be there. So like the kind of strict identity. Yeah, sorry, that's a great point. I should have mentioned that.
Of connected components of that.
Yeah, so objects. Yeah, I wonder if it would be clearer with maybe like a dotted line or something to represent the identity. But this ends up being very useful.
It's actually clearer without it, because
I agree.
There's certain things you can do.
Like
moving things past each other that's not obvious if you did draw.
Yeah, that's fair. Yeah. So yeah, we just don't draw that in. Yeah, great question. Thanks. Yeah, I should have mentioned that. Okay, so this is the multiplication we get. Okay, so now we kind of know we're on the same page with respect to like two categories and string diagrams. We're mostly experts now because we pretty much do know everything there is to know. So now we can get back to the bifunctor question. So this bifunctor theorem concerns families of functors between categories. So what about a theorem concerning, let's say, functors, which I leave a bit vague for the time being, between two categories? I leave it vague because there are lots of notions of functors between two categories. So the question is, what sort of functors shall we consider between two categories? So we originally required a result for pseudofunctors. But for reasons that aren't necessarily clear yet, we kind of thought we might want to capture a bit more than that. Monads there was some similarities with monads we were interested in. So the answer is we made the most general kind we could, lax functors. Okay. So what is a lax functor? So C and D, so now the pink ones are two categories. So let C and D be two categories. So then intuitively, a lax functor, f from C to D, is going to map objects, one cells and two cells, as you expect. So we're going to have functions kind of mapping these things. But composition and units are more relaxed than we're used to. So for every composable pair of one morphisms in C, so notice for a functor, right, if we have f of g composed with f, that needs to be equal to f of g composed with f of f. Now, you might think that when going to two categories, well, that equality, that's far too strict. We should replace that with an isomorphism. And that would give you this concept of a pseudofunctor. But we're going even more relaxed than that. We aren't even asking this morphism to be invertible. So all we're asking is that there is some morphism, some two morphism, which we call gamma and indexed by f and g, which maps f of g composed with f of f to f of g composed with f. And so this we call the compositor. And similarly, we need this kind of relaxed notion of an identity.
Just to be clear, like when you say two categories, like you being like a strict, like the composition is strictly associative.
Yeah, I think. I mean, I'm usually like a bit vague. So, like, what are you working?
You can be vague as coherence, but in your example, just for offhand, what is it? What do you get?
I mean, what are we doing?
I think it's easier constructed.
Yeah, I think. Yeah, I can't remember if we.
There'd be an analogous theory for the weakness, but it can get a bit interesting. Like it's not all just
Yeah. Okay.
Yeah, I think assume it's strict.
Yeah, because like when you everything is coherent, like every weak two category can be is a strict two category, and that's fine. But not every weak functor is equivalent to. So it's at the level of functors that things get interesting.
Yeah, sure. No, that's fair.
But that's fine. You're catering for the most weak functors, even more weak than that's fine. But I'm just saying you have to worry a little bit about the source. I mean, the actual things as well.
So I mean, that's could be interesting to kind of look at more. But we'll just stick with these strict two categories for now. So here we have this thing called the unitor, which is going to relate the identity on f of c to f of the identity of c. So again, which in the one categorical case is just equality, in the pseudofunctor case is isomorphism, and here is just a morphism. So, okay, so turns out that the compositor and the unitor, so I've kind of told you what is the data, but the compositor and unitor need to satisfy some axioms. So in particular, there are three axioms. So I'm going to draw attention to two of them. So the one says that compositors ought to behave like so. I've omitted the subscripts, but the subscripts are such that it makes sense. And the unitors need to behave like so, which is looking a little familiar. We've seen something like this before in the monad case. So this is these are the axioms for monad multiplication and monad units. I'm not going to worry about the other condition. It ends up not being important for our purposes. And okay, so now though, having kind of defined the lax functors to our satisfaction, we can look at this lax bifunctor theorem. So suppose we have lax functors, LC from B to D and MB from C to D for each. So again, indexed by objects of B or objects of C. And we again want that LC of B is equal to MB of C. Now this is maybe a bit surprising that this equality is showing up here. Because maybe we think we could have got away with something like an isomorphism or something, but it ends up being the most natural thing to consider. I think it doesn't work even with isomorphism. I don't know if you remember, Graham, but it's definitely more natural.
To type check.
Yeah.
I think you need to have equality if you want to get the result exactly like.
Yeah, exactly. Yeah, so for certain.
What also matters that fits your example, right? In your example,
it fits our examples, indeed. But we're gonna see the kind of on the last slide. We'll start to see why type E type questions will are important. And yeah, so we actually want equality here. So furthermore, now suppose we have, now this is kind of generalized how we kind of think it should have. So we now have a two-morphism, sigma fg, which goes from LC of f, m, oh, that's probably supposed to be a C2, LC2 of f, MB1 of g to MB2 of g, LC1 of f. So this is just that equality that we had in the first one-dimensional case, but now we've replaced it with a morphism, which, again, not even an isomorphism, just a morphism.
So now you've broken symmetry.
Yeah, basically, yeah. So let's see what happens. Yeah, so now, okay, we want sigma to satisfy certain axioms, and then we're going to be able to construct a bifunctor, P from B cross C to D, as follows. So P of BC is going to be equal to LC of B is equal to MB of C. So again, notice here that having the equality here means that we aren't even making a choice on what to define it. So we might have had a choice and we could have picked an isomorphic one, but already like we kind of see that equality is quite natural for this reason. So P of f comma g is going to equal the right-hand side of this, so it's important. I guess it's the right-hand side. So that's what it does to one cells. And to two cells, it just horizontally composes them. Okay. Now, we also need to describe the uniter, which again, well, this is just the horizontal composition of the two uniters. And the compositor is very complicated looking. So we've got, firstly, we're indexing by like 4 morphisms, and we take this horizontal composition, which is quite nice, and we compose it with this very complicated looking thing here. Yeah, we can actually understand this result a bit better by using string diagrams. So looking at what these things are saying. So the compositor can be understood visually we're going to now draw the L functors in yellow. The M functors are going to be in blue.
Sorry, Peter. So can you please go back?
Yeah.
Are there 2 compositors now?
So we have
because there was a compositor unit on this. There's 3 compositors.
So we got compositors for the lax functors from L, and we've got compositors from the lax functors for M. And so
we also have for the joint.
Yeah. So now we are going to define one for the joint. So we've got to combine these 2 compositors that we have in some way. So this is what it ends up looking like, the compositor, which is the multiplication that we got for applying a distributive law to a monad in string diagram form. So, okay, that's what the multiplication ends up looking like. But what about those axioms that sigma needed to satisfy? So if you recall, I just said that sigma satisfies certain axioms. So let's just quickly talk about those. So those are exactly the axioms of a distributive law of monads. Yeah, so we have this nice, well, at this stage, kind of superficial connection between this Lax bifunctor theorem and distributive laws of monads. Superficial in the sense that the diagrams look the same, but in some sense, there's still certain, there are some differences in terms of what these y's actually are at this stage, but soon we're going to see that we can actually, sorry, there are 2 other conditions that I omit here. They end up just being kind of naturality conditions. So you can see these in the paper, they end up not being important. And so we're going to...
I don't know whether I would say that.
I didn't want to draw out even more. I couldn't fit them on the page. So
what is important? Do they correspond to something on the monad side?
On the monad side, they are automatically satisfied. So that's, yeah, I was going to mention that when I spoke about the monad thing. So they're just automatically satisfied. Yeah, so we just never need to worry about those conditions, basically. So such a sigma we call a distributive law, but now of lax functors. So, or at least families of lax functors. Okay, so let's talk about some applications. So obviously we can recover the usual bifunctor theorem for 1 categories by just considering 1 categories as 2 categories in the obvious way with kind of trivial 2 cells. But we can also get a pseudofunctor result. So suppose we now have pseudofunctors. I mean, I won't kind of go through all of the details. The important difference is when we specify to the pseudofunctor cases, we make the distributive law invertible. And if sigma satisfies the above mentioned axioms, then we'll construct a bifunctor which satisfies this property we were hoping it would satisfy. And furthermore, every pseudofunctor P prime is pseudo-naturally isomorphic to one of this form, where you get the families M and L quite canonically, I think, by just kind of fixing elements. So that was the thing we ended up using, which was nice. But okay, let's look at more interesting applications. So now let's make this a link to distributive laws of monads. So right now it's just apparent, and we have this apparent link. Let's make it precise. So we can view monads as lax functors from the terminal 2 category into D. So this is now monad on D, or in D. So in this case, we have L from 1 to D and M from 1 to D. So now we have 2 monads, and our so this is we've got these 2 lax functors.
I'm very confused. Let's start again. We can view monads.
So you can view monads as lax functors from the terminal 2 category into D, where basically what this is doing is it's picking an object in the 2 category. The identity morphism is picking the endomorphism, and then we get the multiplication and uniter from compositors. And so sorry, this is not our result, to be clear. But so yeah, now in this case, so now let's say we have 2 monads in the sense, right? So they're just lax functors. We can get the original monads by applying the functor to the identity in each case, and then we get the compositor, and the uniters gives us mu and eta.
Now you're talking about 3 categorical stuff there, right?
Well, I don't think we have to go so far as to you can at least reason about all of this purely as 2 categories.
But in principle, you're talking about the 3 categories of 2 categories, and then you got 1 and D are objects there. And then you're talking about.
Though I think there are problems about considering a 3 category of 2 categories with lax functors. I think they don't compose nicely. I think you need to consider some sort of triple category, that ends up working.
But it's true that they're like Hom sets are 2 categories.
Yeah.
Very nice.
But okay, so now if we have a distributive law, so again, remember the S and T are now L1 and M1. So if we have this distributive law from L1 M1 to M1 L1, so these automatically satisfy the axioms. Oh, sorry, I should also mention, before we've been talking about families of functors, but notice here that the families are indexed by the objects of the domains, but these are just one object, 2 categories, so there's only one functor L and M in each case, so we don't have a full family. So we have this distributive law, and these automatically satisfy the axioms of the monad. So kind of from the diagrams you saw, and those 2 conditions that I omitted just end up being satisfied immediately. And so the resulting bifunctor we get, so remember, we're supposed to get a bifunctor out of this, but a bifunctor is you take the product of the 2 things, so 1 times 1, but 1 times 1 equals 1, and so the resulting bifunctor is again the monad. And so I think that this is, if I were to guess why this connection between bifunctor type theorems and monads wasn't noticed, is because it doesn't really seem like we're doing some sort of bifunctory thing, because the 1 times 1 is invisible. Okay, so
to make that precise, and it all comes out to be exactly the things that you got. Okay?
Yeah,
that's nice.
Yeah. Okay, so some further applications. So a monoidal category is a 1-object bicategory. So now consider now the pseudofunctor theorem for, we're going to set B equal to C equal to D, and we're just going to call this A to not confuse ourselves. And for L and M, we're going to just take the identity on A. So then we're going to have that this sigma xy is going to be an isomorphism from x tensor y to y tensor x. And note that the axioms for this to be a distributive law are telling us precisely that this sigma is a braiding. And so hence A admits a braiding if and only if the tensor admits the structure of a strong monoidal functor. So that's a nice application to braidings. Now these are a little, we have some paragraph. We don't really look at these in huge detail in our paper, but for enriched categories, so I think you can view, you can view enriched categories as lax functors from, is it the object, the set of objects as an indiscrete category into V itself. And so in this case, then it basically allows for taking this product of enriched categories in a certain way, where we've got this additional structure. So whether there is something interesting to be done with this idea is something that maybe we aren't sure about, but it seems like there maybe ought to be.
Yeah, so there is a way, like there's already a known way, if you have braided monoidal categories, a way to take these kind of products of enriched categories in this way, and kind of it does reduce to, like our case reduces to that if you use the braiding that you get from the braided monoidal categories. But in the kind of general case, it would like allow you to kind of like have a different braiding for every kind of choice of things, and we don't actually know to what extent. We don't know like whether this is important or not. But
Yeah.
Sounds cool though.
Yeah. And then there's another thing which we think it could have something to say about factorization systems. And so that's because I think distributive laws in the, is it monad of spans? What's the exact set of yards?
Like by category of spans.
Yeah.
The distributive laws of factorizations. A monad is a category, and a distributive laws of factorization.
Yeah.
Strict factorizations.
So yeah, we think maybe there's something to be done.
Really.
Yeah.
Yeah, so some sort of way to combine factorization systems. So yeah, that's something. But that's kind of it for applications. So
yeah, well, I guess yeah. So so in the case of factorizations, like for distributive law of monads, right? You're going to get a it'll take the factorizations and will just give you the underlying category. That's what kind of the kind of composition thing does, right? But in this case, for our case, you consider a more general lax functor into spans, and a lax functor into span by the Grothendieck deconstruction corresponds to like a functor from like A into span corresponds to a kind of functor from something else B into A. So there's it's kind of like a weird kind of version of like index factorization systems, I guess.
Yeah, well, good. Yeah, I don't remember too much about that application, but I'm glad Graham does. So, okay, yeah. So the final thing that I'm going to end with is these links to uncurrying. So, yeah, distributive laws of monads correspond to monads in the 2 category of monads in D. So that's a result. So what we're saying here is that distributive laws are actually just lax1, lax1D. And so in that case, then what we've described so far is a mapping from lax1, lax1D, the distributive laws, into, again, this bifunctor. When we think of this as in kind of the bifunctory forms, into lax1 times 1 into D. And so is there something here, basically? Is this a little more general, or can we kind of generalize this? So one thing that I maybe should have emphasized in this case is that when we have these lax functors, we no longer have this isomorphism between kind of the product, the Hom, like a tensor exponential adjunction.
Tensor adjunction.
Yeah. So yeah, we don't have an isomorphism there anymore. So this is not like trivial, actually. Yeah, in general, you won't have a map going back in general for lax functors. But so what we can do is we can show that there is a bijection between distributive laws of lax functors and this set. Lax B, lax C, D. So right now, just as a set. So because I haven't spoken about what morphisms of distributive law should be, or even 2 morphisms. So, but there is this kind of very natural canonical bijection. There's a way to basically extract all of the data of a distributive law from an object of lax B to lax CD.
Sorry, Peter, I think I'm lost here. What do you mean by distributive law? How can you form a set of distributive laws?
So sorry. So if we go back here, even further back. So here we've just got So anything that satisfies this will be a distributive law. Okay. So we've got the set of all distributive laws, and the data contained in them is precisely equal to the data that we get from lax B, lax C. So what's more is we can find a good notion of a morphism of distributive laws by kind of using how we unraveled the information over here, and kind of thinking about morphisms of lax B, lax CD, and kind of doing a similar process. And so what we end up getting by this procedure is families of op-Lax transformations between the families of Lax functors, and they satisfy the Yang-Baxter equation. So that ends up being important. And so our process, I haven't actually used the word collation till now, but actually in our paper, this process of moving from a distributive law to the bifunctor, we call collation. So we kind of collate all of the Lax functors together into a single thing. So this process of collation is giving us a two-functor from Lax B, Lax C, D into Lax B cross C to D.
Isn't that currying? I mean,
it's uncurrying, I think.
why don't you call it uncurrying?
I think that's uncurrying, isn't it?
Yeah,
I don't know, but why don't you call it uncurrying?
Oh, because currying is what's usually referred to in the other direction.
I think he's saying, why do we call it collation and not uncurrying?
Oh, sorry, I see what you're saying. I guess we called it collation before we had this connect. This was like this connection. This was the last thing we noticed in the paper. I mean, yeah, it's
but also
kind
it'd probably be a bit confusing if you're thinking about them as distributive laws as opposed to elements of Lax.
Yeah, no, it's a fair question. It didn't really cross my mind, but I can kind of see the value in it. But yeah, I'm also not, I don't know whether or not it's the right decision to have a different term for it. But yeah, so we get this. And so again, I just want to stress that we do not, in general, have a map going back from Lax B cross C to D into this. So this just does not hold for Lax functors.
You get uncurrying but not currying.
Yeah, exactly. So this is not in general an isomorphism, and for instance, yeah, one monad can arise from multiple distributive laws to kind of see why in this Lax setting you might not be able to go back in terms of having a bijection. And yeah, when restricting to pseudofunctors, this does become an equivalence again, and collation, well, again, corresponds to uncurrying, but then also we'll have a currying operation. And yeah, that's the talk. So thank you.
Very cool. I love it.
Oh, good.
Maybe there are questions from the people online.
Oh, let me see how to find.
I have a question.
Okay.
So I totally agree with you that the enriched categories case is very interesting to explore.
Mm-hmm.
To add something there, there's also this interesting fact that if you do the Grothendieck construction of the Lax functor that represents, oh no, sorry, this is for another thing. No, it's unrelated. So
don't worry. Yeah.
That part is interesting, but then I have a different question. So.
Okay. Okay, good.
If you consider monads as Lax functors from the terminal category.
Mm-hmm. Yeah.
I think they are connected. When you consider the Grothendieck construction, you should get the category of algebras of that monad.
Okay.
So I was wondering if you can get something interesting relating the category of algebras of the composite of the two monads and the other two via the Grothendieck construction of the Lax functors.
I mean, yeah, I agree. That does sound quite interesting. Yeah. Yeah. Do you have any thoughts, Graham?
I need to think about it.
Yeah. But yeah, a great suggestion. Thank you. Yeah, we'll look at that.
That's true, because like the philosophy is that monads are only interesting because we actually care about the categories of algebras, right? That's what we really care about.
Right.
So whenever you got some statement at the level of monads, you say, ooh, does this correspond? Does the statement also hold, or does it say something interesting about the categories of algebras?
Yeah, so notice this would be, because distributive laws of monads are kind of very well studied.
Yeah,
so
of course,
yeah.
All of these things in terms of distributive laws, in terms of the algebras, certainly people understand.
It'd be nice if
we haven't thought what happened.
Your thing might reproduce that.
Yeah. So yeah, that could be very cool.
Have you seen that paper by Gardner and the co-author? I forgot the name of the recent paper, relatively recent paper about distributive laws for community.
Yeah, whenever. Oh yeah, go on.
No, I just wanted to know if you've seen that paper.
We did look at some papers somewhat recently, like 2 or 3 months ago, but I'm not sure we noticed anything.
I don't know whether we've seen.
I'm kind of, it's a beautiful result, of course. I'm kind of surprised that nobody has looked into the bifunctor theorem for
Yeah,
general.
it was very surprising to us.
Are you the first to do that for moving away from strict functors?
I'm pretty sure we are the first to do at least Lax functors.
Are there?
And this was a few years ago though that we did this. Right?
So
When
yeah,
did we do this?
this was maybe 2022. It was published, so probably we did it in 2021.
Yeah, but for pseudofunctors, I think people must have understood somehow like that there was a subjunction, but I don't think it's written out anyway.
No. There is that one result about currying and uncurrying that was understood for pseudofunctors, I think.
No, that was for lax functors. Yeah, it was kind of a different approach. So there was someone that did some things with this idea of lax A into lax B into C, relating it kind of. They took this idea of lax A into lax B into C, and they said, kind of, can we have like an adjoint to this, which ends up not being product, but being a different weird tensor product thing. Some are related to these like lax gray tensors things. And they have a paper on this, which is kind of related to this, but they didn't think of it as a bifunctor theorem.
Yeah, that's I think the closest we got to seeing anyone doing this.
And is there any chance of doing something for profunctors?
So I guess we'd need like examples to kind of motivate, because yeah, we want like something maybe. Oh, I guess so. Like a profunctor bifunctor theorem, basically.
Yeah, is there a bifunctor theorem?
Not to my knowledge.
Can't you just make op one of the things op or something, and then do this?
No. You start with two
profunctors. Do you mean collate things to give a profunctor, or do you mean we start with profunctor?
Out of two profunctors, you're creating
another one.
I don't know.
Maybe it can reduce to this because a profunctor reduces to a functor.
I mean, yeah. I mean, he's saying that like you have a profunctor from. So yeah, you start with L and R, right? And L was a functor from what B to
D, I guess, yeah.
So he's saying you have a profunctor from B to D. That means a functor from B up cross D intersects.
Yeah.
And then you have a profunctor R. Yeah, you could do this similar thing. Yeah.
Well, yeah. I mean, whether or not, yeah, it will work and will work out. It's hard to say, but yeah, it's definitely something. So yeah, this has been extended to double categories now. So forget Fimich, yeah. So we had thought to do that at some point, but I guess now we don't have to. We weren't too excited to have to redo all of those string diagrams, but because string diagrams I don't think work very nicely for double categories. So
you mean that's replacing two categories with double?
Yeah.
And about enriched categories, do you think you will end up with the tensor product of enriched categories?
Yeah, something like that. A tensor product that depends on this extra data.
Yeah. So it's not a real tensor product because you need extra data to define it. But
we see.
We were just talking to each other like
last night.
Yeah, last night when Peter was doing the slides, that we kind of thought about this question. We were like, wait a second, it's almost a bit more like a semi-direct product, right? Because you take the product of two things, but you need this additional data. But whether or not know to what extent it's actually like a semi-direct product, but it kind of feels a bit like it.
Yeah, if you take the indiscrete category on the product of the two sets, probably you obtain the right thing, right? Like the indiscrete category on the.
Yeah, right. As the base of the lax functors.
I mean, yeah. So for the.
So yeah, I said it better.
For that enriched case, so we do take the indiscrete category, right? But there's still the distributive law that you need to consider that can give like different answers.
I see. Yeah, that's interesting. And I have another question about the uncurrying. To end up with the lax adjunction, say, or not even that?
I think we tried to do something like this, but it never really worked out nicely. We basically weren't able to get anything. I'm trying to remember we had some sort of partial results.
We do have results about the conditions under which you can go back
Okay.
So we do have certain kind of restricted
But yeah, we never were
results,
able
but
to
yeah, we
extend
weren't
it.
able to get it to be an actual adjunction in the general case.
Yeah.
Maybe like in the normal case, tensor. Let's just see that's an equivalence of categories, right? In the category of no, sorry, there's this collection of functions. So that's in the normal case, it's just a bijection of sets. Right?
Yeah.
Am I right? So your thing would be an equivalence of categories. I mean,
Well,
when it's a pseudo
For
pseudofunctors,
it's equivalent.
yes.
and then the question is whether it all gives a nice adjoint equivalence.
Yeah, but as far as we know, no.
But in the last pseudo.
Sorry, the pseudofunction case, yeah, that's
Sorry, pseudo, yes. Lax, no, yeah.
But for pseudo, it does. But you get something in the lax, and it would be interesting to see what you get. Yeah.
Well, you get a functor, but we don't think it has an adjoint.
Yeah, it doesn't have
Yeah, in general, it's not a very nice functor. Yeah.
Is like in the pseudo case, is it a left and a right adjoint?
Constant equivalence.
So yeah. So when you have like an adjoint equivalence, you can ask whether you can ask whether the structure maps obey the coherence equations. I mean, I know that there's some additional questions you can ask. I know it's an equivalence, but are these particular left unit and right unit comaps for the left adjunction related directly to the left?
We're only talking about the functor going in one direction from our general theory, right? So just the fact that it is an equivalence means that you can take the adjoint, like we aren't talking about, we don't have a pair of functors going back that you can then ask whether they are adjoint or not. So we only have the one functor.
But if it's a pseudo functor, I think your theory will give you a canonical thing going the other way as well.
Yeah, I think it does.
Well, you can get that, for example, by taking the adjoint.
It's not just pick an adjoint, but it's actually your theorem actually gives you an actual adjoint. It's not like I'm using the fact, this functor is an equivalence, so I know there exists an adjoint. You're not doing that. Your theorem actually will give you an adjoint functor, and it will give you
well, do you mean our theorem gives the adjoint to the one that's already going backwards?
Your theorem will give you a currying and an uncurrying explicitly in the pseudo-functor case.
I don't think we, like, the kind of distributive law, like collation gives like something going backwards. Like it'll like for free an adjoint going back. Like we had to kind of manually construct it. So it's a little more complicated, I think. It's been a while since I thought about the pseudo-functor case, but yeah, I don't think we automatically get this one going backwards. But yeah, we are able to prove it. Okay, well, is that all the questions? Yeah, thanks. And I see now there's something in the staff room.
Thanks for everyone for joining us. I don't know, do we have another one next week? Do we know yet? Yes. Okay, well, see you next week if you can make it. Thank you. All right, cheers.